Imagine a line of the train cars. Each train car know where the next train car is located. That's pretty much how the linked list work. Today we are going to learn one of, if not the most important, data structure in the computer science, the linked list. Welcome to another video lesson. Today we are starting a brand new series called the data structure. As you may have guessed from the title, our first data structure is going to be one of the most important you will ever learn, the linked list. But before we can understand how linked lists work, let's take a moment to think about how arrays work. Arrays store every element right next to each other in the memory. This makes accessing a data by index extremely fast. However, they do have a drawback. If we want to insert a value into the middle of an array, we need to shift every element that comes after that. Deleting an element has the same problem. In order to fill the space, we have to shift everything forward. As our data grows larger and larger, this operation gets more expensive. A linked list helps solve this problem. Instead of storing our data right next to each other in a single block of the memory, a linked list stores each element inside of the node. Each node holds two pieces of information. The first is the data itself. The second is a pointer that tells us where the next node is located. You can think of each other node as a train car. Not only does this store the same data or the passenger, but it also knows where the next car is. We call the first node in the linked list is the header. From there, we follow each node pointer until we reach the end of the list. The last node in the linked list points to nothing. We call this null pointer. Now that we understand how they work, let's go over the most common operation. The first operation we will look at is inserting the front of the list. This is probably the biggest advantage a linked list have over the arrays. Instead of shifting every element over the one, we just make the new node and point to head into it. Next up is the inserting at the end of the list. We simply traverse the list by following its node pointer until we reach the end. Then attack our new node there. Inserting at a certain position works almost exactly the same. The only difference is we first travel where we want to insert a node. Then we move the pointer so that the new node sits between two other nodes. Searching requires us to start at the head and checking each node one by one until we find what we are looking for. Notice that we cannot directly access to a node at index 5 like we can with an array. A linked list don't support what we call random access. Lastly, deleting a node requires to reconnect a node around it. Instead of shifting everything over by one, we simply remove one node from the chain, and that's really how you insert delete element in the linked list. So when would you use a linked list? If you know your application will be doing a lot of inserting and removing a data, a linked list are usually the way to go. However, if you need a random access to your data, an array data structure is usually faster because array can jump right to that index. Learning about linked lists is a huge milestone. This is because many other data structures use the same concepts of linked lists or link the nodes together using pointers. Stacks, queue, a hash table, and some type of graph all use a linked list in some way or another. Today we learned about the idea behind the linked list, but tomorrow we will code. We will build our own linked list from scratch using C++. We will create our own node and see exactly how they point to one another in the memory. Thank you for watching, and of course, see you in the next video. Happy coding!